Assalamu alaikum warahmatullahi ta'ala wabarakatuh. Bismillahirrahmanirrahim. Ladies and gentlemen, let's continue our hourly analysis program tutorials. In this video, we're gonna complete the definition of the plants. We talked about plants in a previous video, but let's complete it for more information and for the energy analysis calculations. And here we have our plans. We defined the boiler and chiller. Okay, we have talked about the boiler and the chiller. So here is the boiler and here is the generic hot water plant. We talked about that. And here is the chiller, generic chilled water plant. We talked about that. When you see the report, here is the load for the systems you have, and the peak of the plant may not be may not occur at the same peak of the system. So your system AHU, suppose that this has a peak hour and it may not be the same peak hour of the plant. So the plant sizing data may be different from the AHU you use. Suppose that you have a fan coil or any system like this. The total for the plant may differ, and due to the peak of the plant is not the peak of the system. And you can get the peak of the system exactly like what we did in previous videos about generating the reports of the systems. Okay, so in this video we're gonna talk about something. For example, here from any generic plant, from generic chilled water plant to generic steam plant, here if you wanna calculate the cooling or heating loads only without any energy analysis. But for energy analysis, you have to get the chiller plant from remote source steam. If you choose any option from these options, this means that you wanna include the energy analysis. Okay, and you'll find here another or other tabs available: configuration, schedule of equipment, and distribution, and water. Okay, so for generic, we talked about the generic chilled water and the generic hot water plant. So the changeover, what is the changeover? If you have reversed a plant, okay, and you can use it for cooling, and at the same time you can use it for heating, okay, but by the reverse technique. So the changeover plants use reversible air to water or water to water heat pumps to provide chilled water and hot water to coils in a two-pipe system. Okay. Notice here the systems will only be available if you have in your system water cooling or water heating. If it is a DX system, it will not appear. Okay, suppose that go to system and here and central cooling chilled water. Okay, and central heating hot water. Okay, while is chilled water, if it is a packaged rooftop unit, and here go to central cooling air cooled. Okay, and you go to plants, new default system, you will not find it. You will find the other AHU. Okay, so let's do it again. AHU chilled water and general cooling, chilled water. Okay, and not size, so you have to generate a report again. Okay, here in the plants, new default plant. So here are the systems. You can add the systems that will be supplied by water from your plant. Also, you can add this. So for in this tutorial, we're going to talk about the surface hot water for cooling, or I'm sorry, for heating loads. Suppose that we have here a hot water plant. We talked about the systems and we did not talk about surface hot water. Okay, but before starting this, have to assure that this point is okay. Suppose that we have here a system and here two systems, AHU and FCU, and the peak of the plant at June at 2 p.m. Okay, and here is the cooling coil of each system, and here the number of the systems 10 and 10. This is the multiplier. So here is 46.2 and here for 34.4. Okay, let's see. This is the peak also of the AHU is at June 14 00. Okay, the same as the peak of the plant. But if we see the terminal unit or FCU, we find here the total cooling coil is 36 kilowatt, and here is this is July 12.00 and July 16.00. This is the peak, and July 16. Sorry, all of them are on July, but we have different hour. Okay, that's why here is the total 36 kilowatt, but for the plant we only need 34.4 kilowatt. Why? Because the peak of the plant is different. Okay, and the multiplier here is 10 multiplied by this value and plus 10 multiplied by this value will give you the total or the maximum plant load. That's it. Also, you can print view design. You can get the hourly. Also, you can get many profiles and graphs. View, find this, and here is the hourly and the total ton hours. Okay, and that's it. For new default plant, you can read many things about every plant type from the manual. Okay, so you can read it by yourself. So now let's go to surface hot water. So here, if we have plant supplies, surface hot water for washing or any other purposes, we have to check this box. So here the consumption, the maximum rate of this, the maximum rate of surface hot water consumption, you can get it here by GBM or KBT U per day or gallon per person per day. Also, you can change the units from view preferences. Okay, also before I forget, you can here, this is the multiplier that I mentioned. You can make, if you have the system, many systems but with the same loads, you can multiply it to or whatever you want. This means that we have three systems with the same loads and another system. Okay, so whatever with this, So this plant supplies. Okay, click cancel. New preferences metric and go to plants. Default plant. Generic service. So here is liter per second the total, and kilowatt hour per day, or liter per second, liter per person per day. So here the maximum rate, and here the flow and the consumption. So you can check out all what you need here. Also, the usage schedule is very important. You can create new schedule, fractional, like exactly what we did before. And if you already have it, maybe exactly like the people schedule or any other schedule, you can get it. So here the design temperature at which the hot water should be supplied for washing machines or anything. So we have to determine it here. And here the average cold water supply. What is it? So the average cold water supply defines the temperature of cold supply water makeup water from the municipal water system entering the SHW system. It is used with hourly SHW demand at the design and the design temperature above to calculate SHW load. Okay, so after that we have here the distribution. Here for the distribution, the pipe heat loss factor, you have to estimate it, percentage of heat loss from pipe work. It's between the heat exchanger and the point of consumption. It's according to the pipe length or the piping length and the degree of the isolation. For more information, you can get it from here. Also use distribution pump. If we use a distribution pump to distribute water to the consumption points, you have to get the input power. So this circulation pump input power, kilopascal or kilowatt. Okay, like this. Here is the it's from pump. The pump is used to distribute hot water from the storage tank or the SHW heat exchanger to a tankless system to the SHW points of use. Okay, so the input power defines the pump performance in terms of head, foot, WG or kilopascal, pump power per unit flow, okay, or the pump input kilowatt. Also, you have to determine the mechanical efficiency and the electrical efficiency. If we have this pump as a recirculation pump, we wanna have all the time water, like at hotels or hospitals. You can check this recirculation pump use as recirculation pump, and here you will not be able to determine the pipe heat loss. It will be calculated automatically by airline's program. Also for pump cycling, in a recirculation system, if the distribution pump runs continuously, uncheck this box. Okay, the distribution pump will then run 24 hours a day regardless of demand levels. Okay, so here this is the pump cycling continuously, uncheck this box. Okay, and if instead the distribution pump cycles on demand, check this box. This is if there is demand. Okay, and in this case, the distribution pump will be off for any hour with zero SHW demand and will be on otherwise. And of course, delta T defines the temperature drop in a circulation system between the start and the end of a circulation loop due to pipe heat loss. Okay, So if we have stored hot water, storage tank to store the hot water, we have here the tank volume. You have to get it, and the minimum temperature that is needed inside the tank maybe 45, and if it is here 50, so if the temperature will be lower than 50 or it reaches 45, the system will run until it becomes 50 again. So the hot water temperature will vary from 45 to 50. Also, the loss factor, it depends on, it may be a percentage or it may be watt per liter per Kelvin, according to the size or the volume of the tank and the difference in the temperature difference between the design temperature and the average cold water supply. If we have pasteurization as an option to kill the Legionella bacteria, here it is not a good kind of bacteria. It affects our health due to the stored water or for a long time. So we have this option. So period here 7 days. This means that you will use pasteurization every 7 days, one time every 7 days. Okay, and the pasteurization duration will be 24 hours, and it will start at you have to choose the starting time and at a specific temperature. This is suppose that the pasteurization temperature will be 70, so the water will be at 70 Celsius for 24 hours. Okay, then after 24 hours the temperature will decrease to be 50, the design temperature. This process it is used by another or an external heater. Okay, so you can auto size that heater, or if you know this capacity, you can input it. Okay, so this is what we have talked about. Auto size heater, and here defines the capacity of the subliminal electric heater used for pasteurization cycles. And prioritize service hot water resupply. Sometimes it is not economical to use the heating, central heating and the surface hot water at the same time. But why? Because both systems are not compatible with each other, or they do not have the same peak, or for any other reason. But suppose that if you have very cold weather and you need to the central heating for the zones, and also you need the surface hot water, so you do not have to check this box. But if you want to prioritize surface hot water resupply, check this box, and you can use two methods. Here by schedule, you can create new schedule. You can use the FT schedule that we have talked about. And if you use this, the surface hot water will only be used if the FT schedule is unoccupied, and the central heating for the zones will be used if the FT schedule or the profiles shows that there is occupation. Okay, like we have here occupied. If it is unoccupied, the surface hot water will be used. If it is occupied, it will be used for the central heating. Okay. Also, you can use outdoor air temperature if it is suppose that this outside is lower than 13 Celsius, so the central heating will be used, or the hot water will serve the central heating. But if it is above 13, okay, it will be used for service hot water. Also, if we have here in the systems change over, okay, we will find here third when OAT, the outdoor air temperature below this, the cycle will not used sometimes for cooling and sometimes for heating. So here you have, if it is 13, so if when the outdoor air temperature is below 13, the cycle will be used for the heating process, and if it is above 13, it will be used for the cooling. Below, for changeover plans when the serve combines space heating and SHW loads, this third option is offered. The challenge with this type of plant is that during the summer cooling season, the plant must change from cooling mode to heating mode to satisfy SHW loads. When this option is selected, a threshold, okay, threshold OAT temperature must be specified. The plant will give priority to space cooling loads when OAT is warmer than the threshold temperature. The plant will give priority to SHW loads and any space heating loads when the OAT is colder than this threshold temperature. After finishing this, click OK, unable to OK. Have to save input data, invalid input exists. Red. Okay. Oh, I'm sorry. It's not specified. Okay. And you can print design results. So you find here, like we have shown, the system cooling coil load for each system, and maybe different from the peaks of the plant itself. So and here heating plant sizing data, okay, the maximum plant load here, the cooling plant, and here are the heating plant sizing data. Okay, and here the coincident heating loads for February. Okay, and here coincident surface hot water load 2.8 kilowatt. And here are the hourly chiller load profiles from July to July. Okay. So here the plant formation and the cooling plant sizing data, and notice that load occurs at July 1500, and here is the loads and the heating plant sizing data, and here is the maximum plant load and watt per square meter for area cerebral plant, maximum pasteurization load. Notice that this is very important to know to get the heater capacity. Okay, so this is the heater capacity. That's what's very important to get this report, and so on. And here the you can get the peak of this plant. Notice it's at July 1500, on July 1500, it is the maximum. Okay, and here's the total. Okay, now ladies and gentlemen, after finishing these things, the generic types, you will be able to generate your cooling or heating loads only without the energy analysis. So now it's about time to use the energy analysis. If we use chiller plant up to remote source steam, you have to know the differences between them by clicking on F1. Here you will find, like we have just said. Okay, you find here changeover plants and chiller plant. Okay, but there are now for energy analysis. So notice that if you have here generic, you will find general systems, and chiller plant you'll find systems and configuration, schedule of equipment, distribution. We're gonna find out what about cold water. So chiller plant and the remote source, you'll find here only the distribution, and heat recovery, you'll find this. So according to your selection, this will be determined. Okay, let's start with the chiller plant. Also for the system, you can choose the systems you need to add and the number of them here. You can click like that, 1 or 6. If they have the same settings and cooling and heat loads. Also, no surface hot water, of course, because it is a chiller plant for cold water. So now it's about time to use this configuration. So if you're here, equipment size, you can use auto-sized capacities. It will be calculated automatically by the software or you. So notice, and here are the chillers, the quantity, the number of pearl chillers. You can put 2 or 3, up to 12. Okay, up to 12. And if they are more than 1, suppose they are 4, you can make they are equally sized, okay, or not. Here is auto sized capacities, and here if we use user specified capacities, we'll find here also the quantity, but it's also auto sized here, or equally sized. We make it 3. Okay, you can here put also the capacity oversizing factor is a safety factor for this operation. So you can here make if they are equally sized, or 40 40 20 between the 3, we make it 2. We find many percentages. Okay, this is all sized. You make it user, you will only find the quantity. All sized equally, we make it 4. Okay, we make it 5. So we make it 3, we make it 2, and so on. So here is the safety factor or the capacity oversizing. When you specify all sized chiller capacities, you must also define the oversizing factor for plant capacity. For example, if you specify 15%, program will automatically determine the plant capacity as peak coincident coil load for air systems served by the plant plus 15%. Note, when you specify user-defined chiller capacities, the S is not relevant and is therefore disabled, like that. Okay. The cooling controls have to control the plant or the chillers have here sequenced with parallel load chiller, high plus low loads, and equal unloading. They are sequenced. What does this mean? And click F1. We have here all chillers in the system are sequenced in the order they are defined in the schedule of equipment tab. Okay, so chiller 1 turns on first. If its capacity is not sufficient to meet the load, chiller 2 turns on, and so forth. Chillers are turned on until the total capacity is sufficient to meet the building load. While running, chillers share the building load by running at the same part load ratio. The following example, as we see here, or this, we find here the building load, the total building load 1500. So the chiller 1500, 500, 500, both all of them will start running. If this is the total building load in tons, all of them also will run. But if the load of the building is 1000, no need to use the third. It will not start running, only chiller 1 and chiller 2. If this is the total load, also the same. If there's 500, no need to use two chillers, just one chiller. This is the total, exactly the same. Okay. If you have a sequenced with part load, the chiller, high plus low loads, this means that we have here with this control, all the chillers are sequenced in a conventional manner described above for sequenced control, exactly like this, but with the part load chiller acting as the last chiller, this is the part load tons, to turn on. However, when the capacity of the part load chiller alone is sufficient to meet the building load, this, all other chillers turn off and the part load chiller runs alone to serve load. Therefore, the part load chiller runs for high and low load conditions and is off for intermediate load conditions. So like this example, if we have here the total, so find that 500, 500, and this is the part load, all of them must run to meet the peak or the total. Okay, if we have only 1000, no need for the part load, 800, no need for the part load, 500, no need for the chiller 2, and for the part load, 400, the same case, 200, no need to use the many chillers, only the part load chiller can be used, and 100 also the same. For the unequal unloading, with this control, all the chillers in plant operate for all loads. There is no sequencing of chillers as occurs in the other control schemes. Exactly like this. So we have here 300 tons. All of them will use 100, 100, 100. 240, it will be 80, 80, 80, and 60, 60, 60. If there are 60, it will 20, 20, 20. Okay. For the leaving chilled, cold chiller water, here is the leaving chilled water temperature control. If it is constant or reset by outdoor air temperature schedule or reset by load constant return water temperature, we have here. So it offers three options. Okay, with this control, the design of LCHWT is held constant for all plant operating hours or reset by OAT schedule. This control, the plant LCHWT is adjusted according to a reset schedule based on outdoor air dry bulb temperature. Control points for this schedule are defined by the remaining inputs in the section. Reset by load RW T. With this control, the plant LCHWT is adjusted based on load. Okay, here is based on the plant load. LCHWT is adjusted to maintain the return water temperature at a constant value. So here, if you use constant, you have to set the design leaving chilled water temperature, reset by OAT schedule. Here, example by reset. Okay, so design LCHWT is equal 44 Fahrenheit used when OAT greater than 65, maximum LSCHWT 54F used when OAT less than 35. So as shown in the figure, when the outdoor air temperature is 65 Fahrenheit, okay, outdoor 65, okay, or warmer or more. Okay, the plant controls LCHWT to design value 44. Okay, so if it's lower than 35, you use it here. So the plant LCHWT will be 54. Okay, very okay. And what if it's between 35, the outdoor air dry bulb, between 35 and 65 here, so the LCHWT will vary between these degrees, okay? So along a linear control profile. Another example, so design LCHWT is 7. This is when OAT above 20, like this. Okay, above 20 it will be 7 Celsius. So maximum LCHWT it will be 12 if when OAT below 5. So it is below 5 it will be 12. Okay. Again, this is the Arabic HAP manual of the engineer Osama Atif. Okay. So for the last option, reset by load constant RWT, you only have to get the design LCHWT. This is the leaving chilled water temperature and the maximum leaving chilled water temperature. You have to get both. Also, you can use free cooling if you have cooling towers in the loop. Click on this. So we have here strainer cycle. So the strainer cycle, when the return water from the cooling tower is sufficiently cold, return water is diverted into the chilled water loop to serve air handling unit cooling coils, and all the chillers are turned off. Because fouling of the chilled water piping and heat exchanger is a concern, a strainer device is used to filter the water as it flows from the condenser loop into the chilled water loop, hence the name strainer cycle. So the operating LCHWT for a system is 44 Fahrenheit. For a certain set of operating conditions, the cooling tower is able to produce 41 Fahrenheit return water. The chillers in the system are all turned off. Cooling tower water is diverted into the chilled water loop and is blended to provide 44 Fahrenheit water to air handling unit cooling coils. Another thing or another option here is non-integrated water side economizer. What is this? We have here this loop, okay? So a plate frame heat exchanger is positioned in parallel with the chillers in the plant. Okay. When return water from the cooling tower is sufficiently cold, it is diverted through the plate frame heat exchanger where it cools water in the chilled water loop, and all chillers in the system are turned off. Okay. Non-integrated refers to the fact that the economizer only operates when it can meet the full plant load. Okay, here is the deal. With this control, either the economizer meets 100% of the load or the chillers meet 100% of the load. But the economizer and chillers do not operate simultaneously. The third option here is the integrated water side economizer, like figure 2. A plate frame it extends position of the return water pipe upstream of the point where the return water mixes with the water from the common pipe. When return water from the cooling tower is sufficiently cold, it is diverted through the plate frame it extension where it pre-cools. Notice pre-cools the return water and thereby reduces the load on the chillers. As the return cooling tower water temperature drops, the plate frame heat exchanger will be able to handle progressively more of the plant load until the point where all the chillers are off and the heat exchanger handles 100% of the load. So integrated refers to the fact that the economizer can operate simultaneously with the chillers. It can therefore provide partial as well as full free cooling and therefore yields greater energy savings potential than the non-integrated type of water side economizer. So for example, the operating LCHWT for a system is 44F. An integrated water-side economizer is used and provides an approach of 3 Fahrenheit. For a certain set of operating conditions, return water temperature is in the chilled water loop is 51 Fahrenheit and the cooling tower return water temperature is 46F. The plate frame heat exchanger can therefore pre-cool return chilled water from 51F to 49F. This reduces the entering water temperature for the chillers and therefore reduces the chiller load. So in the heat exchanger, the approach for the plate frame heat exchanger here defines the performance of the plate frame heat exchanger is used in a water side economizer. The approach is the difference between the temperature of the water entering the heat exchanger minus the temperature of water in the chilled water loop leaving heat exchanger. So for a given set of flow conditions, 41F return water from the cooling the tower entering the plate frame heat exchanger will produce chilled water leaving the heat exchanger at a temperature of 44F. Therefore, the heat exchanger approach is 3. So you can make it here 3 or 1.7 according to the conditions. Okay. Note, gentlemen, that for plants containing air-cooled chillers, free cooling inputs only apply for plants containing one or more water-cooled chillers. If you are entering a plant with all air-cooled chillers, ignore this input. It will not have any effect on system calculations. So the last thing here is the cooling tower configuration. One tower for each water-cooled chiller, or one tower shared by all water-cooled chiller in the plant. So with this configuration here, one tower, a separate cooling tower or dry cooler is paired with each water-cooled chiller in the plant. There is a single condenser where loop with the manifolded pumps, the cooling tower or dry cooler and its condenser pump stage on and off with the corresponding chiller. On the schedule of equipment tab, you will specify one cooling tower or dry cooler for each water-cooled chiller in the plant. If one tower shared by all water-cooled chillers in the system with this configuration, one large cooling tower or dry cooler is shared by all water-cooled chillers in the plant. Condenser water flow for the all water-cooled chillers is combined and piped to and from the cooling tower by dry cooler. One condenser water pump drives flow through the plant. So when used in a plant where chillers are sequenced on and off, enhanced performance can be achieved when several chillers have been sequenced off, since a larger heat transfer is available for a remaining number of chillers to use. However, the gain in heat transfer efficiency is sometimes offset by the increased condenser water pump power. So plants consisting of air-cooled chiller, what about them? The cooling tower configuration input typically only applies to the system containing one or more water-cooled chillers. For plant consisting of air-cooled chiller, water side economizer can be modeled by specifying one tower shared by all water-cooled chillers in system, and then specifying a shared cooling tower. So this cooling tower will serve to pre-cool return water in the chilled water loop to reduce or eliminate the chill load. When conditions allow free cooling, okay. On the other hand, if you are modeling a plant of air-cooled chillers without water-side economizer, this cooling tower configuration input item is not used and has no effect on plant calculations. Okay, now gentlemen, if we use hot water plant, okay, like this, or steam boiler plant, okay, you will find these things, okay. So hot water plant, fan systems, okay, this water configuration, like we have said, you can use auto-sized capacities or user-specified capacities, and here is the quantity, and here is the percentage, like this. Okay, exactly, capacity oversizing factor and heating controls, the same things, and constant or reset or these things. And also you can get these ranges, and also like exactly like what we did for the chillers, but here for the hot water. Okay, so if you have auxiliary heating like this, check the box if the plant has an auxiliary heater. Inputs in this section will then be enabled. Auxiliary heaters are typically used for hot water plants with air to water heat pumps. As outdoor air temperature decreases, capacity and efficiency of the heat pump can decline to a point where either the heat pumps cannot meet plant heating load and operating the heat pump becomes too inefficient. In both situations, an auxiliary heater can be used to supplement plant heating capacity to meet the plant demand, or to handle the full plant load and allow the heat pump to be turned off. In auxiliary heating is selected, the auxiliary heating device will be specified in the schedule of equipment tab. So if we have here allow simultaneous auxiliary, what is this? Check the box if the auxiliary heater is allowed to operate simultaneously with the heat pumps. Checking the box models a plant in which the heat pumps serve as first stage heat, and when they are unable to meet the plant load, the auxiliary heaters turn on as second stage heat to meet the remainder of the load. The plant runs in this way until the COP or outdoor air temperature trigger is reached. If either of these triggers are specified, once the trigger is reached, the plant switches to 100% auxiliary. So you have here trigger COP is below this, okay, or COP or outdoor air temperature is like this. Switch to auxiliary below this outdoor air temperature. Also here switch to auxiliary below this COP value. Okay, so in the other plans we have here auxiliary heat pumps run, heater runs, but not both. To model this type plant, leave the box unchecked. For this control, once the heat pump capacity is insufficient to meet the plant load, the heat pumps turn off and auxiliary service 100% of the plant load. The plant controller will also turn the heat pumps off and use auxiliary heat to meet 100% of the load if the COP or out air door temperature trigger is reached, if either of these triggers are specified. Okay, so the H, so you can use this or use this or use both, okay, according to the design. HX approach The HX approach, if the auxiliary heater is a boiler and the heat is transferred to the hot water supply loop via heat exchanger, check this box and specify the approach for the heat exchanger. If the auxiliary is an electric sleeve heater or is a boiler which supplies hot water directly into the hot water supply loop, leave the box unchecked. Okay. So what about the trigger here, COP box? This check this box if the plant controls that will turn off the heat pumps when their operating COP drops below a threshold and runs 100% auxiliary heat below this threshold. For example, the box is checked and COP below 2.5, like this. Okay, what does this mean? 5 in below value 2.5, specify the heat pumps will turn off when their operating COP falls below 2.5. So OAT, check this box if the plant has controls that will turn off the heat pumps when the outdoor air dry bulb temperature falls below a specified threshold temperature. For example, if the box is checked and we make this 15, okay, 10 specified the heat pumps will turn off when the OAT is colder than 15F and auxiliary here will serve 100% of the load. Notice that here is 15 Celsius. Okay. And here for HX approach you have to get the approach, heat exchanger approach temperature value. For the heat recovery plant, gentlemen, we have here systems also. Surface hot water and configuration. We have here the equipment, auto sized or user specified capacities. Okay, for auto size, if we make it to equal sized or the percentage, if we make it 1, just 100%. Okay, and here the capacity or sizing factor. Okay, 3. Okay. Also for the boilers, you can make it 1 boiler, 2 boilers, up to 12. Okay, up to 12. Make it 3, the same. And here is the cooling controls and here the heating controls, the same like we said, and also you can check it out from F1. Okay, 300, 100, 100, 100, and also this exactly. So you can check out these things in details if you want. I think this is the same thing. Okay, also we can here get the design LCHW Celsius when OAT above and the maximum. Okay, and 1 tower for each or 1 tower shared. For here the equal unloading or sequenced, notice if we make this 1 here only equal unloading, if we make it 1 equal unloading, if we make it 2 we get sequenced or these things again, also these options. For the heat recovery heat exchanger in condenser loop and many options. So here click F1 to find many categories. Dedicated heat recovery chiller in parallel with cooling only. A chillless plant consists of 1 or more air-cooled or water-cooled cooling only chillers in parallel. Dedicated heat recovery chiller is positioned in parallel with the cooling chillers and acts as the load chiller. The DHRC condenser is connected to the return water pipe in the hot water system. The DHRC is controlled to operate when heating demands exist in the hot water system. When operating, it contributes cooling to the chilled water system and simultaneously rejects heat to the hot water system to reduce the load on the heating system's boilers, thereby reducing boiler energy use. Heat exchanger in condenser loop. This plant consists of one or more water-cooled chillers in parallel injecting heat to a condenser water loop using cooling towers or dry coolers. Heat exchanger is connected to the condenser water pipe downstream of the chiller condenser water outlet and upstream of the cooling tower inlet. So this heat exchanger is also connected to the return pipe of the hot water supply system. The heat exchanger therefore transfers heat from the condenser water loop to the hot water system. In order to successfully recover heat by this method, the condenser water temperature entering the heat exchanger must be higher than the temperature of the return water in the hot water system. So this requires the chillers to be operated at high entering condenser water temperatures, which result in higher chiller energy use. This heat recovery approach is only viable when the heating savings generated by heat recovery exceeds the additional energy costs for operating the chillers at high condenser water temperatures. So the third is the dedicated heat recovery chiller condenser and condenser loop. This plant consists of one or more water-cooled chillers in parallel rejecting heat to a condenser water loop using cooling towers or dry coolers. A dedicated heat recovery chiller is positioned with its evaporator in the condenser water pipe downstream of the chiller condenser outlet and upstream of the cooling tower inlet. The DHRC condenser is in the return water pipe of the hot water system. Therefore, this DHRC acts as a water-to-water heat pump to transfer heat from the condenser water loop to the hot water loop. Also, the chillers with the superheaters, this plant contains air-cooled or water-cooled chillers, one or more, which are equipped with these superheaters. This superheater is a refrigerant gas to water heat exchanger that is upstream of the condenser. How this charged gas from the compressor flows through the superheater and transfers its heat to incoming water. The superheaters or the superheater is designed and operated so it will not cool the refrigerant gas to the saturation point. While this superheater can generate high temperature hot water, it can only capture sensible heat from the refrigerant, so the amount of heat recovery is limited to the amount by which refrigerant gas has been superheated above saturation. So you have to be careful when you choose your system, and you have to know how it works. Once the refrigerant gas leaves the superheater, it passes through an air-cooled water cooled condenser and rejects the remainder of its heat as it would in a conventional chiller. The fifth type is chillers with double bundle chillers. This plant contains water-cooled chillers, one or more of which have a double bundle condenser. This is a condenser with two separate water circuits. One circuit is connected to the cooling tower heat rejection loop. One circuit is a heat recovery circuit connected to the hot water system. When a heating plant load exists, water flows through the heat recovery circuit and the heat is rejected to the hot water system. When no heating part load exists, water flows through the heat rejection circuit and the heat is rejected to the cooling tower loop. Also, we have here the sixth type, the chillers with heat recovery condensers. This plant contains air-cooled chillers. One or more of the chillers are heat recovery chillers and have dual condensers, a refrigerant to air condenser or for normal heat rejection, and a refrigerant to water heat exchanger for heat recovery. When a heating plant load exists and the hot water supply temperature requirements can be met, the heat recovery chiller uses the refrigerant to water condenser to reject heat to the hot water loop. When no heating plant load exists or sufficiently hot water cannot be generated the heat recovery chillers uses refrigerant to air condenser to reject heat to the atmosphere. So gentlemen, also as a good idea for you, you have to check out in details, more details, and get the drawings of these systems by searching in Google, and to get many information, a lot of information about these things to exactly know how it works. Okay, and of course you can here use what you want. Okay, but if you use the heat exchanger in condenser loop, you have to get the heat exchanger approach temperature value. Okay. Okay, now gentlemen, for the schedule of equipment, and here suppose what you have chiller systems. Okay, configuration. We make auto sized capacities, and here quantity 2 for the sized whatever. So here the schedule of equipment here is the sequence chiller 1, chiller 2. You have to, you may make the sample, get the sample. Here's auto, and here the cooler flow rate and the condenser flow rate, and which cooling tower. Maybe the sample cooling tower that we have already in the library. You come here and cooling towers for the sample, so you can get it. Also, you can get here the chiller or the sample chiller. We have here a sample chiller. If we delete this, okay, and go to plants, new chiller plant, systems, configuration, to, okay, schedule of equipment. You can create new chiller. Okay, why? Because we have here auto sized capacities. If we make user defined, can check to can get your chiller already that you have defined in the library. If you choose it, you can get the information and the cooling tower. Also, you can get the sample cooling tower in the library. Okay, and its flow rate. Okay, why? Because if we have also another chiller, you can create new chiller. Or suppose that you have many chillers, different chillers in the library, you can choose many of them here. And for each chiller, you can choose different cooling tower, of course. Why? Because here every chiller has its own cooling tower, okay? But just a tutorial, so I do not have many cooling towers here. Okay, suppose that this cooling tower is different from this, and this chiller is different from this. So no need to, there is no shared equipment. If you have the chillers, all of them have the same information, you can make all equipment the same. Okay, look. Right, also we can make, suppose that this is like that, we make all equipment the same, we'll find this like this. Okay, suppose that we have here one tower shared, user defined. You no need for this information because it's one cooling tower. Okay, you can use one cooling tower, and here are the total full load capacity and total cooler flow rate, and total the total condenser flow rate, and total cooling tower flow rate. Okay, what if we make auto sized? Okay, auto sized, you have to create new chiller, or you can use anything. Use sample. Okay, just an example. So we find it auto, and this is the cooler flow rate according to the information of this sample. And here also you can use anything you want. Okay, so here as an example, so this is the equipment, and this is they are sequenced. This is chiller number 1, chiller number 2, chiller number 3, and everything we need is here. And the step layout, schedule of chillers. Each row in the table contains data for one chiller. Okay, and this is the sequence and chiller name, selecting existing chiller or creating new chiller. You have to know when can I use this and when cannot I use this. Also the full load capacity, the design cooling capacity for the selected chiller. The cooler flow rate is the flow rate through the evaporator cooler of the chiller at the full load design condition. The condenser, listed water cooled chillers, it is used to quickly determine whether the flow rates of the further chiller and its cooling tower match. Also the cooling tower name with the cooling tower configuration, 1 tower per WC chiller, each row shows the name of the cooling tower. Okay, so here the tower flow rate. Okay, and make all equipment the same button on the tower left, like what I have just showed to you, is used to quickly make all chillers and towers in the plant the same. Okay, therefore if your plant consists of a number of identical chillers and towers or dry coolers, you only need to select a chiller and tower for one row of the table and can then use the button to quickly copy the selections. Okay, also you can increase these things by make it 5, notice, and so on. And the total full capacity, sum of full load capacities of the chillers in the table. This item contain data only if the user defined capacities option is selected for the plant. Total cooler flow rate, sum flow rates in the table. Also define the units in GPM or liter per second. Total condenser flow rate, the sum of condenser flow rates for chillers in the table. Okay, estimated maximum load, the peak load for the plant. This item only appears in design calculations were previously run for this plant. When using the user-defined capacities options, it is useful to compare this maximum load with the total full load capacity. Okay, above to verify the plant has sufficient capacity. The shared equipment also, we have the shared cooling tower, and also we have the steam source. When one cooling tower shared by water cooled chillers option is selected on the configuration tab, a single selection of a cooling tower or dry cooler is made here. Also, this drop contains all previously defined heat rejection equipment, like what I have just shown to you. Okay, so here is this. Also, the steam source, when a plant contains a steam absorption chiller or an engine chiller which uses steam as its source, this item appears in the shared equipment section. This is used to specify the source of steam for the equipment. In this drop-down lists remote source steam option to model use of waste steam or steam from a district system. The drop-down also contains all previously defined steam boilers and the create new boiler option. The latter option is used to create new steam boilers, save it, and automatically link to the plant. So here the chilled cooling tower. Also, gentlemen, from the changeover plant, something that you have to see is the changeover delay. You can use this thing if you want this input specify the delay imposed when the plant changes from cooling mode into heating mode. This delay may be required because of the physical limitations of equipment or control rules. For example, an interval of time may be required to allow supply water loop temperatures to rise from cooling mode levels to neutral levels. to avoid introducing unusually cold into the chiller's condenser. During the delay period, the plant will not operate, so plant loads will not be served, and no energy will be consumed by the plant equipment. Okay. So if a delay exists for this change, specify it in minutes. If no delay is required, or you want not, or you want to model the idealized plant operation where no delay exists, specify 0 minutes. Also, here schedule of equipment, and this is the changeover, recovery. For the heat recovery, this is the configuration and the schedule. You can get the chiller and then the boiler and these things. You have to know how to get these things. Also the same. So, okay, and here use a chiller, and here you can use your boiler. Okay, suppose that is a chiller. Sorry. Okay, and sample boiler, and here is the cooling tower. Why? Because here one, if you make it shared, you will not find cooling tower, so a cooling tower will be here. Okay, and change over the hot water plant. Okay, no problem. And remove source, surface hot water, schedule. Okay, you can make schedule, surface hot water, and steam boiler. Okay, now we know what's going on, I think. And the remote source steam. Okay. Okay, now, ladies and gentlemen, the distribution tab here, to enter here for the chilled water supply, the distribution system, and the primary loop pumps, and the fluid priorities. If you have here the type, we have three options: primary only, constant speed; primary only, variable speed; primary secondary, like this, variable speed, and this. Okay, so for primary only constant speed, you have to know this. So the distribution tab is used to define the distribution system and the controls for chilled water and hot water plants. For steam plants, it defines the pipe heat loss factor. So the appearance of this tab changes depending on the plant type, and like the other things, depends always on the type and the distribution system options that are selected. So figure 1 here, it shows the typical tab contents for a chilled water plant. Hot water plant would have the same content, except that the sub-tab title would be a hot water supply, and I'm gonna see this in the next couple of minutes. Okay, shows here. So is the chiller water and hot water. Okay, so the distribution system, we have here three. So the primary only constant speed, the system type covers the following two operating scenarios. Look at this system. From here, chiller 1, chiller 2, and pump 1, pump 2. The primary only constant speed with three-way valves, and here the air handling units, as you see. So contains a single chiller, heat pump, or boiler, or it contains multiple machines, and it uses equal unloading control schemes. The distribution system consists of one constant speed pump, okay, paired with each chiller. For each chiller, 1 and 1, and the other pump, heat pump or boiler in the plant. The pumps circulate a constant flow of water to air system coils. Three-way valves are used to regulate flow through the coils. Because of the constant speed, constant flow nature of the system, the pumps operate at their design point for all operating hours. So it's very important for you as a designer. So this configuration is shown here. Also, a plant contains multiple chillers, heat pumps, or boilers, and uses one of them of the sequencing control options. The distribution system consists of one constant speed pump paired with each chiller, heat pump, or boiler in the plant. Two-way valves are used to regulate flow through the air system coils. The results in variable flow in the system because the constant speed pumps are used. Each pump rides its pump curve as flow varies. Care must be used to ensure the sequencing of the chillers, heat pumps, or boilers will prevent flow from dropping below manufacturer recommended minimum flow rates. So it's very important for you to know these things. This is very similar to figure 1 below, but with two-way valves and on the air handlers. Okay, so this figure 1, as you see. Okay, the other option. Okay, the other option is primary only and variable speed. Okay, one variable speed pump or a gang of variable speed pumps in parallel circulate water through the system. Two-way valves are used to regulate flow through air system coils. A differential pressure sensor, like this, measuring pressure between supply and return legs of the system, controls pump speed to maintain a constant differential pressure. Due to this control, primary pumps ride the system curve as flow varies, like figure 2. Okay. Also, the third, we have primary, secondary, variable speed, as you see, secondary. One constant speed, okay, one constant speed pump is paired with each chiller, heat pump, or boiler in the system. These constant speed pumps maintain a constant flow through the individual chiller, heat pump, or boiler legs in the primary portion of the system. Therefore, each primary pump operates at its design point. A separate variable speed pump or gang of variable speed pumps in parallel drives flow in the secondary portion of the system. Two-way valves regulate flow through air system coils. A differential pressure sensor, like this, measuring pressure between the supply and return legs. The secondary system controls the secondary pump speed to maintain a constant differential pressure. As a result, the secondary pump rides the system curve as flow varies, like this. So, gentlemen, you have to know how does the system work and how many pumps, how many differential pressure sensor, and these things. Just you have to know the basic idea. Okay. After finishing selection, here is the coil delta T at design. So the coil delta T at design, so for chilled water systems, this item defines the temperature rise for water flowing through the air system cooling coils at the design condition. For a hot water system defines the temperature drop for flow through hot water heating coils. So this delta T is used in simulations of variable flow pumping systems to determine heat and how flow through coils varies when two-way valves are used to regulate flow through the coil. For standard conditions, it is assumed that the valve varies the flow as load changes to maintain this coil delta T. Okay, so you have to get this delta T if this is chiller or for the hot water. Okay, pipe heat gain factor, what is it? For chilled water system, pipe heat gain is computed as the percentage of the total cooling coil load for air systems served by the plant. Okay, so you have to get the total coil cooling coil. You have to get it for hot water system. Pipe heat loss is calculated as a percentage of the total hot water heating coil coil load for air systems served by the plant. Okay, so you have to know this percentage. And pump performance units, you can get it kilo pascal or kilowatt or watt per liter per second. So here also you can change the units. When pump head is specified, the program automatically determines the pump input power from the head. If you use kilopascal, flow and mechanical electrical efficiencies. If you use watt per liter per second, when pump watt per GPM specified, program automatically determines pump input power from the W per GPM or W per liter per second specification and the pump flow rate. If you use kilowatt directly, when pump motor kilowatt is specified, it's directly use simulation calculations. So I think this is the recommended. You can get it easily. Okay. So here primary loop pumps, you can use the input power. Notice that if you make it kilopascal, kilowatt, okay, and here are the mechanical efficiency and the electrical efficiency, okay. Here for the fluid that is used, maybe fresh water, or you have to select the fluid in the circuit. Okay, and here is the fluid density and the specific heat capacity. You can change them, and also you can, if you do not have the fluid, suppose that we have here a fluid, also this will be changed. Also you can name, okay, and you can change what you want. Here for primary only variable speed, but before this, suppose that we have here 3 chillers, schedule and distribution. We have here primary pump constant speed. You can get the chiller 1, chiller 2, chiller 3, okay, and get the information for pump for equipment. So every chiller has its own pump, and you can input what you want. So as you see, for primary only variable speed, the system uses only one pump, and if you have many pumps, you have to give the equivalent one curve, just to get the one curve for the whole system of the pumps, and you get why, because there is shared. Okay, as you see, you have here, you can get 3 here. You can get shared, and you get the input power, mechanical efficiency for the shared system. Okay. Here the control head. You can click F1 to know here, as you see, for the primary loop pump for equipment, and here the mechanical efficiency. Okay, for the control head, you have to give the differential pressure to control the variable speed pump. Also, for the minimum pump flow, you have to give the minimum pump flow that you need to control, or not, or for the variable speed pump, and this is a percentage of the design flow rate, and it is maybe 30% from the nominal flow rate. Also, for the minimum chiller flow, as you see here, it is you have to get the percentage or the minimum percentage of the flow of the chiller, and the percentage also from the nominal flow rate or the design flow rate or the full load flow rate, the flow rate. Okay, and here for the chiller, also for the hot water plant. Okay, here minimum flow allowed, also the minimum flow allowed for the pump and the chiller, and also of this hot water you have to give the minimum boiler flow, and also there's a percentage of the full load. Okay, so notice that for the minimum pump flow it is a percentage from the design flow rate of the pump, and for the chiller it is according to the full load, percentage from the full load, and for the boiler a percentage from the full load. So for the primary, secondary variable speed secondary, also the same way can get the information from primary loop pumps. If you have here the three chillers and the shared auto sized like exactly what we have said, and here the control head and the minimum pump flow for the secondary, I think. Okay, and notice that if we have one, okay, we'll find here chiller one, and here, okay, shared, and we have five, find here five, and so on. And here also the control head, system head that is independent of flow, and here the minimum flow allowed. Okay, we make this for the system head also, and minimum flow as we have just said. For the condenser water, to if you have cooling tower, okay, schedule. Suppose that we have a chiller, the cooling tower, okay. The condenser water, the pumps for the cooling tower or the condenser, the pump for the condenser. Okay, so here configuration, pump control, constant flow, constant speed, variable flow, variable speed. Okay, here, so the pump control. If you have here constant flow, you will find only pump performance units, kilopascal, like we have just said, and kilowatt, and watt per liter per second. Okay, so if you have 5 chillers, you have to get these things, and you have to get what you want, and get the mechanical efficiency and the electrical efficiency. Suppose that we have only one schedule and distribution condenser. Okay, if you have a variable flow, variable speed, you have to get the minimum flow, pump flow, and its percentage for the design flow rate, and the static head. So the static head applies to condenser water testing using an open circuit cooling tower, describes the portion of the condenser pump head due to the vertical rise in the condenser pump loop. This input is only enabled when variable flow, variable speed pump control is specified. So with open circuit cooling towers, the condenser water flows in an open loop. The presence of the static head causes the zero flow point on the pump system curve to correspond to the static head, rather than passing through the zero flow, zero head point. So this has a significant effect on pump performance when operating at reduced pump flow and speed. When using closed circuit cooling towers, dry coolers, or JU well fields, condenser water is a closed loop, and static head should be set to zero. So, gentlemen, you have to know the details of the system you use and to get the information required for these steps. Okay, because you have to be careful when you use these inputs. Okay, gentlemen, here also for the remote source, you'll find system and distribution, and for the heat recovery, can get this. The configuration is cooling and heating. Here the schedule. Hope that we have this. Okay. Okay, you find here the distribution. You find chilled water supply and the hot water supply. Notice that here is the please you have to know the coil delta T for the chiller and the pipe heat gain. Here is the called delta T design for the boiler and the pipe heat loss. Okay, also the same things. According to your selections, these inputs are changed. Okay, arena the condenser, water. Okay, for the changeover plant, actually you have source water with the configuration, schedule. Also have this distribution. Okay, and source water. So source water tab is used to define the source water loop for controls on pump performance for a changeover plant using water source reversible chillers or a hot water plant using water-to-water heat pumps. This tab is divided into two sections as shown below. Exactly. So we have to get the constant flow, constant speed, or variable flow, variable speed. Okay, exactly what I've just said. We'll get the minimum pump flow and the static head for this water system. Exactly. And here's the water loop. Okay, if you have many chillers. Okay, chair. Find here constant. Here the chiller, model sized, configuration. Okay, for user specified. Okay, so as you see, it depends always on the things you get or input. We refer the distribution and the source water. Okay, for the pumps, look, it is shared. Okay, make it variable. Okay, so ladies and gentlemen, it's always according to the type of the system you use. Okay, surface hot water. Okay, and according also to the inputs here, all the size or what schedule according to the equipment, and these things will be changed. And here we have a cooling tower like this. You'll find condenser water. So after finishing all these things, you can click OK. Okay, and you can get the sample plant. Okay, I think that we have covered a lot of information. I think I hope this helps you. Now we have just finished our tutorial. We talked about all kind of plants, boiler, chiller, and other plants for the energy analysis. So this is the end of the plants. The next tutorial, if Allah wants, we will talk about buildings, and it will be the end of this series about hourly analysis program in details. The next tutorial we're going to talk about buildings and how to generate the energy analysis reports and the other important things that's related to the buildings. We have talked about how to generate the design results of the plant here. Okay, you can get this. As you see, you find many things. Okay. So the next tutorial we're gonna talk about buildings. Thank you very much. I'm sorry it is a long tutorial, but I hope it works with you. So thank you very much. Assalamu alaikum warahmatullahi wabarakatuh.